Well, I appreciate the opportunity to be here today. It's been following along with the Soil Health Nexus webinar series, so it's just kind of an honor to be here and present to the group. So what I want to talk about today, based on the title here, obviously, is evaluating soil health and soil carbon dynamics in Midwestern cropping systems. So you're probably wondering, why is an engineer talking about soil and soil health? Well, that's kind of a long story, but let's just say I really like soil and we'll leave it at that. So what I want to do today is basically go through two different studies that were done. So there was a soil health study in 2017, and then more of a long-term study looking at soil profile total carbon levels over an 11-year period. And then I'll just wrap up with some thoughts on, kind of what we're seeing at that site and maybe some of the reasons why we're seeing what we are. Just to give a little context here for where this research was done. So this was at the Northeast Research and Demonstration Farm. So you can see kind of north central, northeast Iowa area there. And so all of this soil data actually came from one of our drainage water quality research locations. So there's 36 1-acre plots at this location, and there's basically 6 different management systems in place. I'm not going to talk about any of the water quality data today, but I will go into some detail on some of the different soil measurements that we've been taking at that location. So the soils there, just to give you some context, these are mollisols, so prairie-derived soils, loams and silty clay loam textures. Organic matter at the surface tends to run in the 3 to 4% range, just under 30 inches of precipitation per year, and then a little over 4 of that actually goes out through the drainage line. So average of the last 15 years, about 15% of the precipitation we get at that location goes out the drainage line. So I'm going to start here with the soil health study that was done in 2017. So our overall goal here was just to look at these different management systems we have in place there and see if we could pick up any differences looking at some soil health indicators. So we've got a cereal rye cover crop treatment. We have some plots where the 30% of the stover was baled off and removed in the fall over an 8-year period. We can compare swine manure application to a spring UAN application, and then we've got some tillage versus no-till comparisons. So we're looking at total carbon, total nitrogen, bulk density, potentially mineralizable nitrogen, and wet aggregate stability in this study. Pretty basic setup. This is a randomized block design there. So there's 3 plots in each treatment. So corn, soybean, there will be 3 plots in corn, 3 in soybean each year. We only sampled the corn plots in this study, but basically what we did is took 3 cores from each plot. So this is a 3-inch diameter bulk density sampling ring to a depth of 6 inches. And then all of this data was plugged into the soil management assessment framework. So that's basically just a program that looks at different soil health indicators and comes up with an individual indicator score and then compiles all of those into a composite soil quality index. Here's the management systems that are in place there. So I'll just briefly go through the notation. So SU 168, that's a spring UAN side dress treatment. The 168 is the nitrogen application rate. FM stands for fall manure. So everything with FM is a fall manure treatment. NT stands for no-till. And then after the no-till is the number of years that treatment has been in no-till. So we've got a 2-year no-till system. We've got a 10-year no-till system that also has had a cereal rye cover crop. So the plus R, that's our cover crop treatment. That's also been in place over that 10-year period. And then we've got a treatment that's been in no-till for 38 years. So all of those are corn soybean rotation. We've also got 2 continuous corn treatments. So one of those is where we had our stover removal over the 8 years. And then that one also had a one-time gypsum application in 2015. So the minus S there, that's our stover removal treatment. So there's a lot of data here. I'm not going to try to plow through all of it, but I just want to highlight some of where we did see significant differences between treatments. So if we start with total carbon, on both a percentage and a mass basis, we did see lower carbon levels where that stover had been removed. So that could be due to that stover removal in part. But there's also some maybe legacy effects from prior management changes that could be in play here too, that I'll talk a little bit more about later on. If we look in our corn soybean rotations, we did see a significantly higher total carbon level in that 38-year no-till treatment compared to the 10-year no-till with cover crop. And again, looking on a mass basis, so now we're taking into account bulk density here and not just the percentage carbon. So again, the 38-year no-till was significantly higher compared to the spring UAN treatment. If we look at total nitrogen, again, that 38-year no-till treatment had significantly higher total nitrogen on both a mass and a percentage basis compared to all of the other corn soybean rotation treatments. And then bulk density was kind of interesting. So what we found here was that all of our no-till treatments basically had higher bulk density in general compared to the treatments where there was tillage. So both the continuous corns and that spring UAN, there was tillage there. So in our no-till treatments, we are seeing higher bulk density. Now that's not uncommon. A lot of other research has found that you tend to have higher bulk densities with no-till, but that does have some implications for how these soils are scored that I'll talk about more as we go. We did look at potentially mineralizable nitrogen, didn't see any differences between any of the treatments for PMN. And I also just listed carbon to nitrogen ratio here. That wasn't something that went into the soil quality analysis, but I was just curious what those were and if there were any differences. We did not see any significant differences in C to N ratio between any of these treatments either. So then the question came up, we did do this sampling around the 1st of June. So this was a spring sampling. And so a lot of these samples tend to be taken in the fall. So there was some question, well, maybe we shouldn't have done it in the spring. Our thinking there was, you know, if we're concerned about soil health, we want to know what's the health of that soil or how is that functioning while that crop is growing in the field. So it seemed like a more representative sample to do that, you know, early season versus at the end of the season after you've harvested your cash crop. So that was why we did it in early June. But out of curiosity, we wanted to come back and look at that bulk density again in the fall, just to see if maybe that timing was a factor there. So if you see the 10-year and the 38-year no-till with the ampersands there, they were statistically lower in the fall compared to spring. But overall, it really didn't change the results. We still generally saw higher bulk density in the no-till versus the tillage plot, whether they were sampled fall or spring. Now, if you look at the two continuous corn treatments there on the right, those results actually flipped. And I don't have a good explanation for why that happened other than possibly some sampling error. So these cores were sampled similarly to what you see in the picture there. So it's a hammer sampler. You're pounding a 3-inch diameter ring into the ground. That's got a steel plate on top of it. So you have to be very careful when you're pulling these samples. You know, if you hit that one too many times, you just compacted your bulk density sample. So could have been some issues there with some inconsistent sampling. We also looked at wet aggregate stability. So if you're not familiar with what that is, I'll just briefly go through it here. So essentially what you do is you take a given quantity of soil, so 100 grams of dried soil. In this case, you re-wet it so that all of the samples are at a consistent moisture. And then you place those into sieves and you submerge them in water and just slowly oscillate those sieves up and down. So what we're trying to get at here is how stable are those aggregates when they're submerged in water. So there's 3 different sieves here, greater than 2 centimeter, aggregates will stay in the top sieve, 1 to 2 centimeters in the middle sieve, and then the bottom sieve is 0.212 to 1 centimeters. And we also did extract the sand out of those fractions after we had separated those out, because a sand particle, technically is not an aggregate. So we wanted to get at, what was just the aggregates without the sand as well. So here's the results from that sampling. I'll start with the blue bars. So that's our greater than 2 millimeter fraction. If you just look across at the letters there, they're all the same. So greater than 2 millimeter, we did not detect any significant differences between these treatments. If we look at the 1 to 2 millimeter fraction, the 38-year no-till was statistically higher than all of the other ones that you see there circled in red. So we did see a difference in the 1 to 2 fraction, and also the 0.212 to 1 millimeter fraction, the 38-year no-till again was statistically higher than the spring UAN. We just look at total aggregation, the gray bars here, so all aggregates greater than 0.212. Again, that 38-year no-till was statistically higher than our continuous corn treatment where we had the stover removed. But just in general, if you look at the plot here, we didn't see any dramatic differences between these different treatments. And that surprised me a little bit. Going into this, I would have thought, after 38 years of no-till or after 10 years of no-till with a cover crop, maybe we would have seen some, more of a shift towards larger aggregate sizes in that case. But at least in this research study, we did not find that. So now I'm going to briefly go through our soil quality index scores. So this goes into the soil management assessment framework program. So if we look at aggregation, no differences, they all scored very high. So basically these soils are already very well aggregated, relatively speaking, and no differences detected there. If we look at bulk density here, now the continuous corn treatments actually have a higher score. So in this case, a higher index score is better. So a score of 1 indicates that soil is basically functioning at its full potential. So a lower bulk density is considered to be good for soil health. So if you got a lower bulk density, you have a higher score in this program. So higher scores for the continuous corn treatments. Now, if we look at total carbon, we did see higher scores in the 38-year no-till and the continuous corn where there was no stover removal. So not a big surprise there. That's sort of what we would expect to see, but a little bit disappointed in what we saw in the 10-year no-till with the cover crop treatment. There was actually the lowest when we looked at total carbon, which kind of surprised me. And then the overall soil quality index score, when you factor in all the different indicators we looked at, the continuous corn plots with annual tillage actually came out on top. And there's some different reasons for that, in this program. But just to summarize what we found here, the potentially mineralizable nitrogen, that was our main biological indicator here. And it ended up not being very useful. We didn't detect any differences. So we're mainly looking at physical and chemical indicators where we're seeing some slight differences in this program. Higher bulk density in the no-till, again, that's been found in other research, but that does reduce that soil quality index score. So it's maybe a bit of a disadvantage to the no-till in that case. The stover removal does look like that possibly impacted that total carbon at the 0 to 15 centimeter depth. But there is some prior management on those plots, going back 30 or 40 years. It could have affected that I'm going to show on the next slide. We did see greater total nitrogen, higher score for total carbon with that 38-year no-till. So that was not terribly unexpected. But soil quality index scores are actually the highest in our continuous corn treatments with annual tillage, which I was not expecting to see. And that was because of the higher total carbon and the lower bulk density. So I suspect that the total carbon numbers potentially be driven by just the high residue input in these annual corn systems. It's just a lot of residue being incorporated back into the soil. Bulk density is probably driven by the tillage effect. We're maybe seeing a slight trend towards greater aggregation in that 38-year no-till treatment, but that's a little bit arguable. It's just kind of some shifts around the margins and the different fractions. And probably the most surprising to me was that the cover crop after 10 years, we didn't see anything significant. It didn't, really improve those indicator scores relative to any of our other treatments. So had some results here we weren't necessarily expecting to see. So why didn't we see more treatment effects? Well, anybody who's done soil research knows that trying to measure these, living, changing dynamic systems is just difficult. Sometimes you don't get the results you expect to see. And some of the indicators we use probably weren't ideal. Again, pretty much all soil research will tell you that the more cores you have, the more replicates you have, the better. We could have used more cores to help with our statistical significance. And it's also important to keep in mind, this is just a snapshot in time. So this was just a one-time sampling event in 2017, and trying to use that to look at, could we detect whether prior management affected that? But we didn't do any repeated sampling over time, which would be very helpful in trying to pick up some trends. More biological indicators also would have been helpful here. We had mineralizable nitrogen. Total carbon sort of gets at biology in a roundabout way, but we did not look at microbial biomass carbon or any enzyme indicators, which you can also incorporate into this soil management assessment framework program. We didn't look at PLFA or any of the other newer, soil biology tests that are out there. So mainly just physical and chemical indicators here. And then I think it's a fair question to ask here, looking at that bulk density, a higher bulk density in no-till doesn't necessarily mean that your soil health is worse. That's not an uncommon thing to see, but you may very well still have better infiltration, better aggregation, other things with no-till that we would consider that to be a healthier soil, even though the bulk density is higher. So it's maybe not a fair apples to apples comparison there. And the other thing I would just mention here that, we're already dealing with very fertile, healthy, relatively healthy prairie derived soils here. And so when you have a soil like that, it's just much more difficult to, change your soil health significantly and to increase it over time. Whereas, if this was a much more degraded soil, it tends to be easier to see more rapid changes and more dramatic changes. So it could be the reason that we're not seeing more treatment effects is just that these soils are already in relatively good condition. So now I'm just going to quickly jump into the second study. So we also, on these same plots, looked at soil carbon, total carbon, going down to 1.2 meters or 120 centimeters. So 3 cores from each plot, and they were analyzed with the dry combustion method. So again, the same plots here, same treatments, but now what I'm showing you is the management on these plots going all the way back to 1978 when these drainage plots were first put in. And I'm showing the nitrogen management back to 1999. So you can see right off the bat, we have some major challenges here. We've got all kinds of confounding variables. We've got tillage, especially changing over time from different systems, because every so many years they implement some new treatments on these plots, for water quality and other reasons. Crop rotations have changed over the years. So I can just come right out and say it, we can't with any certainty say that, there are any differences between one system or another, and, what that might be attributed to. There's just too many confounding variables here. But what we did find with this still ended up being very interesting. So what you're seeing in this table are the areas, broken out by depth where we saw a significant increase in total carbon over time. And now this is within plot. So I'm not comparing one treatment to another. Statistically, we did not see any differences between any of these treatments as far as that rate of change in total carbon over time. So no differences between treatments, but within treatment, we are seeing significant increases in total carbon over time, from 2007 to 2017. So I've got those bolded in red. You can see at the surface, lots of variability, didn't really see any major trends there. Nothing that we could say is significantly changing. But as you start working deeper in the profile, you see more and more treatments that are showing an increase in soil carbon over time. Now this was a little bit surprising, not some studies have showed this, other studies have showed the opposite. So we are seeing an increase, especially deep in the profile. And this is pretty important because a lot of studies don't tend to look deep in the profile when they're doing these soil carbon studies. So pretty interesting results here, especially that 60 to 90 centimeter depth, basically all of these treatments. So it didn't matter if it had manure or was corn soybean versus continuous corn, didn't matter if it was a cover crop, didn't matter if it was no-till. They're pretty much all showing increases in carbon deep in the profile. Just to give you a snapshot of what that looks like when you plot it out, this is just all of the treatments thrown together at the 60 to 90 centimeter depth, plotted over time. And so you can see a pretty, I don't know if I call it dramatic, but you can definitely see an increase over time there in that trend line. So then the question was, okay, if soil carbon is increasing, how much? How much carbon are we talking about here? So this is just an estimate. I want to stress that we do not have bulk density on these deep cores. So we have to make some assumptions here to get at a carbon mass number. But if we make some somewhat reasonable assumptions, we say bulk density is 1.35 and it's not changing over time, because that could affect it. If your total carbon's going up, but your bulk density is going down, those two could cancel each other out. So we have to assume it's relatively stable. And I only factored in where we saw a significant increase. So anywhere that it was not significant at P is 0.05, I just assume no change. So with those assumptions, these plots are accumulating about 1,300 kilograms of carbon per hectare per year, or 1,160 pounds. So that's a lot of carbon. That's more than other studies have shown. But I think the main difference is we're looking much deeper in the profile here. So a lot of the literature reports are, from 100 to 1,000, somewhere in that range in similar systems. But most of those are only looking 30 to 40 centimeters deep. So they're really missing a big part of what's going on here. I think that's why we're coming up with a little bit different result. So just to summarize a little bit of what we're seeing and maybe some thoughts about why, we have a lot of what I call management-induced variability near the surface. So we can't really pick up any significant changes there in total carbon. But you get below 30 centimeters in depth and pretty much all of these treatments are showing a significant increase in total carbon, which was a little bit surprising. So the implication here is, and we're not the first research group that's said this. It's been repeated many times now in the research, but we just absolutely must be looking at least a meter, if not deeper, in the soil profile if we're going to understand the soil carbon dynamics. The other thing to really keep in mind, especially with these plots we have at the Nashville location, is with all these prior management changes, that can take decades, for those changes. Say you go from moldboard plow to no-till, for example, it could take many decades for that change to sort of propagate its way through the soil system and for that to come to a new equilibrium. So some of what we're seeing could be due to that, but there's definitely some implications here. Other research, just the other day, I saw a study from Wisconsin, their cropping systems trial there, they're looking 3 feet deep and they're seeing a loss in soil carbon to 3 feet in all of their treatments, except where they had pasture. So we're seeing the opposite results here. I'm not exactly sure why. It could just be different soil types, but just some thoughts on it here. Is it possible that these high residue input sort of conventional systems, we would call them, continuous corn with annual tillage, could it be that they're having a similar effect on soil carbon relative to our cover crop systems or soil health systems? Is this something we can replicate elsewhere? I don't know. Other sites, they're showing a loss in soil carbon. Is this a legacy effect? So I mentioned those prior management changes. Could it be that what we're seeing is just from changes that happened 20 or 30 or 40 years ago and they just haven't worked their way through the system yet? That is a possibility. The other thing, there's a lot of interest now in soil carbon studies and paying farmers to sequester carbon. But, if we make the assumption here that in our conventional systems that carbon is being driven by, residue input, a lot of that's likely to be particulate organic matter or POM versus, more of your mineral associated organic matter that you'd be probably more likely to see in a more biologically active system, with no-till and cover crops and soil health practices. So should we be making a distinction there? Because that particulate organic matter, basically the microbes just haven't gotten around to chewing it up yet, and what's going to happen to it when they do? So I think that's an open question. Most companies that are looking at getting into these carbon markets and paying farmers to sequester carbon, they're just looking at total carbon or total organic carbon. They're not making that distinction between, where is that carbon stored? And one other point I would make here is that back in 2015, there was a paper published by doctors Jessica Veenstra and Lee Burris from Iowa State. And they took deep cores down to 1.5 meters around the state of Iowa here, looking at systems that were undisturbed versus farmed and what change happened over a 50-year period. And they did see a loss in soil carbon at the surface, but they also saw an accumulation of soil carbon deeper in the profile, similar to what we're seeing at Nashua. And their explanation for that was that it's quite possible that carbon's actually dissolving at the surface due to potentially rapid changes in pH from fertilization or other things, and then it's leaching down through the profile and precipitating out as that pH comes back up when you get deeper in the profile. So that's another possible explanation for what we're seeing. Also, again, I mentioned this site is tile drained, which is going to improve that water flow. So we hear a lot about carbon going up into the atmosphere, but what about carbon that's dissolving and leaching down into the profile? From a soil health aspect, that's bad. We want that carbon to stay up by the surface. But if we just want to lock carbon away and keep it there, that could actually be a good thing if that's what's happening. Because once that, gets into the deep profile and turns into a carbonate, it's probably going to stay there for quite some time. And just a few thoughts or discussion points to wrap up here. Again, we hear a lot about soil health and carbon sequestration. In my mind, those are often sort of conflated or confused. What happens at the surface is incredibly important for soil health. But when you look at the studies that are actually out there, long-term studies of soil carbon at depth, we can't necessarily say for certain that, those systems are automatically going to be sequestering carbon. So I think we need to be, a little more mindful when we're talking about soil health and carbon sequestration. That could be, sort of two different things. It's very clear in the research that these soil health management systems are increasing carbon cycling, which is a great thing. A lot of our systems are starved for carbon, but we can't automatically assume that that's going to increase carbon sequestration because some studies just aren't showing it. There's a lot of reasons to try to improve soil health. I'm a huge proponent of soil health and regenerative ag practices and principles, but carbon sequestration may turn out in the long run to not be one of the reasons to do this. So we just, I think as an agricultural community, we want to be a little careful we don't sort of get out in front of our skis, so to speak, on this, and have a lot of farmers thinking that they're going to get long-term payments for these carbon sequestration efforts. But it can be, depending on your location again and your context and all of that, certain places it can be very difficult to increase soil carbon over the time, and it can take longer than some people might be anticipating. So just some food for thought there. I'll wrap it up. I just want to very quickly acknowledge some of the funders over the years for this project. I'm kind of just the messenger here today. I'm a very small part of a much larger, ongoing research that's been happening at the university there and at the Northeast Research Farm. So Dr. Helmers in particular, he was my major professor when I did some of the soil health work. Other people on my committee, lots of people to acknowledge and thank here, all the staff at the Northeast Research Farm that have been collecting all of this data over the past many years. So with that, I'll wrap it up. I appreciate the opportunity to present to the group,